Good afternoon, everyone. I'm Ed Remus, the Social Sciences Librarian at Northeastern Illinois University, and on behalf of the NEIU Libraries, I'd like to welcome everyone to this event. Before I introduce our moderator, I'd like to take a moment to thank those who made this event possible. Funding for this event has been provided by the NEIU Physics Department, the NEIU Library Foundation, and by Heterodox Academy, a nonprofit organization that fosters open inquiry, viewpoint diversity, and constructive disagreement in higher education. If you're a member of the NEIU community and you're interested in helping to plan and organize events such as this one, please email me to learn more about getting involved in our Heterodox Academy campus community here at Northeastern. On behalf of the NEIU Libraries, I'd also like to mention that a recording of this event will be available on the NEIU Libraries YouTube channel by the end of the week. I will now introduce our moderator, Orin Harris. Orin did his PhD work on the ATLAS experiment at the Large Hadron Collider before switching fields in 2013 to using bubble chambers to search for dark matter. He is a member of the PICO and SBC collaborations, and he's an associate professor of physics here at NEIU. Thank you. Orin.
Thanks, Ed. All right, so let me introduce the topic of today's discussion. The standard model of Big Bang cosmology accounts for a variety of astronomical and cosmological data within a framework that assumes that general relativity is correct and that a large proportion of the mass in the universe resides in particles we have so far been unable to detect. Scott Dodelson will represent this perspective. Scott Dodelson is a Fermilab scientist and professor in the Department of Astronomy and Astrophysics at the University of Chicago. His primary research interest is in analyzing data from cosmic surveys to inform our understanding of dark matter, dark energy neutrinos, primarily within the standard cosmological model. An alternative perspective, represented today by Stacy McGaugh, is that in place of dark matter, we consider a modification of how ordinary matter interacts gravitationally. Stacy McGaugh is a professor in the Department of Astronomy at Case Western Reserve University. His primary research interest is the study of low surface brightness galaxies, which connects more broadly to his work in using astronomical and cosmological data to test the predictions of dark matter versus modified Newtonian dynamics. I've asked each of our panelists to present their position for 20 minutes each. After this, each will be given 10 minutes to respond to any points raised by the other. Then for the remainder of the event, which we want to end at 4:30 Central Time, I will moderate questions from the audience. I will not be moderating the chat for questions, and we will not use the raise hand feature. If you have questions, please use the Q&A feature on Zoom. Scott, you will go first, and I turn it over to you.
Great, thanks very much, and thanks for inviting me. I didn't realize this was part of this idea to bring competing ideas together and try to discuss them civilly. So that's something I'm kind of aching for today. So I'm really privileged to be part of it, and of course, known of Stacy for a long time. So honored to be on the same stage, so to speak, as him. So let's get started. We're talking about dark matter modified gravity. Start with a couple of caveats. I think we all have to be humble when we're discussing this topic. It's kind of crazy to think that we can apply what we've learned in the lab or anywhere else to describe the entire universe, which is much bigger than any one little experiment we've done. And many, many people, very smart people and cultures have tried in the past, and at least we believe they have failed miserably. So, the notion that what we have today is correct, and in 1,000, 2,000 years, people are going to say, oh, they got it right. I think we have to be wary of being that arrogant. So we must be humble, and then I particularly must be humble about this topic because I don't know that much about it. Stacy's kind of the world expert in MOND. I got interested in these theories about 20 years ago, but only spent about 5 years or so studying them, and I know very little about their current status. And then also, I think as you'll see emerge, we come at these things from different perspectives, small scales and large scales. And on the small scale side, which is kind of the domain of galaxy formation, I've only really dabbled in it, so I'm only really dangerous. I'm not really knowledgeable. So those are my caveats. Having said that, I want to try to articulate the great successes of modern cosmology and explain to you why many of us are convinced that there is dark matter in one form or another. So here's the background. Light travels at a finite speed. So when we use telescopes to take pictures of what the universe look like, we see the sun as it was, 8 minutes ago. We see galaxies as they were billions of years ago. And actually, the furthest thing we see is this. Can you see my cursor, by the way? Yeah, good. Okay. The furthest thing we see is this thing called the cosmic microwave background, which is 13.7 billion years old. It was when the universe was only about 400,000 years old. And this is a picture of the microwave background. It's photons that reach us when electrons and protons combine to form neutral hydrogen. After that, the photons traveled freely through space. So they're reaching us. They're all coming from a shell, a given distance from us. Photons further away haven't reached us yet. Photons closer passed us by already. So this is a shell, a 2D shell projected onto the screen of what the universe looked like when it was only 380,000 years old. And the remarkable fact about it, it was incredibly uniform. That basically, if you took any one spot on the sky, it would have almost exactly as many protons, neutrons, and photons as any other spot, to 1 part in 10 or 100,000. Incredibly uniform. As opposed to maps we make today, I've worked for the last 10 years on the dark energy survey, and the universe is very inhomogeneous. You know that because you're all living in rooms where the density is 30 orders of magnitude larger than the average density in the universe. And the dark energy survey maps this out over an eighth of the sky, and it makes this remarkable map of the mass. It's very inhomogeneous. So we've gone from a very homogeneous map to a very inhomogeneous map. And I'm going to argue that we can learn quite a bit from both each of the maps separately and from the way that one evolved into the other. A metaphor for this is consider this primordial map of the United States. So there are overdensities in the population. There are 50 people per square mile on the coasts here. There are vast voids with very low population density. So if we were smart enough, we could learn quite a bit about the constituents of the country at that time. There were these urban centers and the rural areas. Probably could guess that farming was going on around here. There was trade, and makes sense, it's along the water. So there must have been, shipping lines, and we were trading with our European partners. So you can learn quite a bit about the constituents and basic laws governing what was going on at the time just by looking at maps. Similarly, if you look at the United States today, well, the overdensities have grown. Now it's in Manhattan, it's actually about 50,000 people per square mile. And we have all these cities that's propped up all over the place, but still have large empty spaces. And again, if we study these carefully from the perspective of a sociologist or a political scientist, we can infer something about the constituents and about the laws governing not only the country today, like how closely cities are oriented with respect to one another, but also how we got from there, the early United States to here. So in some sense, we're in the same situation with cosmology, and the fiducial cosmological model that Orin alluded to. Get rid of this thing. Sorry. Extracts information about the constituents and the laws in the universe and explains how we evolved from early to late times. And if you take nothing else away from this whole talk, I think something that both Stacy and I will agree on is that 1,000 years from now, people will agree with this statement, that the way we got here is gravity amplified small overdense regions that are apparent in this map into the rich structure we observe today. That is, if it was a small region in space that was slightly overdense over the course of 13 billion years, more and more matter accreted there until a galaxy formed there, and then stars and planets and people, etc. So, oops, sorry. How can I go back? Can I not go back? Okay, good. So that's that I think Stacy and I will both agree on. But now let's talk about this fiducial cosmological model. And again, before diving in, a couple of caveats. It turns out cosmology is not exactly like studying the evolution of the United States. We get only one chance to see light from a given region. You can observe New York City over many different times, but you can only see a hot spot in the CMB once. If their galaxy formed at that spot, CMB is the cosmic microwave background, that initial map. If a galaxy formed there later, we wouldn't see it yet. The light would not have reached us yet. So we get one chance to see every spot in the universe. And that means no cosmological theory can predict that we should see X if we look in a given direction. That's just not what theories do. Rather, cosmological theories or models make predictions about the distribution of matter, how likely it is to find matter clustered, to find galaxies which typically are in overdense regions near one another, how many really big things we should see. The models did not predict where we should see them. So to sum up, cosmological models are very good at predicting statistics, which turn out to be very non-intuitive. I mean, you have to spend a while trying to sift through them. It's not that they're intrinsically hard, it's just we're not really used to discussing them. And but those statistics, as I'll try to argue, really are the strongest evidence for this model. And the other comment that I'll make, and this is a place where there might be some space between Stacy and me, is that we cannot make predictions on small scales. For example, no model predicts that I'm sitting in this room, or that this building exists on Earth, or that Earth exists, or that the sun exists, or even that our galaxy exists. And so no cosmological model can be the best thing that cosmology does is makes predictions when you smooth out like rooms this size and make predictions on large scales. Okay, so let's dive into some of the observations. So this fiducial model, which I'll call lambda CDM, the DM stands for dark matter, which is what we're debating. It's just in stunning agreement with tens of thousands of observations. Here's just a smattering, and I'll get into details on a few of them in a minute. So let's first discuss the statistics of the cosmic microwave background. And the first point is they're very easy to predict. And the reason for that is, remember, the universe was very homogeneous back then. So that what that means is that the theory is linear. Linear theories are very easy. So we can make very, very accurate predictions for what which is called a spectrum. And essentially what it is, it's the temperature variance. So the mean temperature is 0, but the fluctuations in temperature, how they vary with angular scale. And I try to get you used to something that we do in cosmology. We plot large scales on the left and small scales on the right. And so what you see is, what you can actually barely see are the data points, these green points here. We've been taking measurements of this spectrum over the course of the last 30 years or so. And we have these green points, which is just remarkably accurate. They're just terrific measurements, very, very small anisotropies in the microwave background. On top of that, I've overplotted the prediction of the fiducial cosmological model. And you can see it agrees just tremendously well. The width of the line is thicker than the error bars. So it's just remarkable. As an exercise, I tried taking out the dark matter from that model, and you see it just does not agree at all. It's just way, way off. So this in itself gives us just a tremendous confidence in the idea that dark matter gives an excellent explanation for this set of statistics. This is thousands of data points. Actually, recently, the Atacama Cosmology Telescope extended this result, and they're not the only one. The South Pole Telescope and others have extended it to even smaller scales. This plot is slightly more technical, but it conveys the same information from large angular scales to small angular scales. These large 10-meter telescopes have extended the scales to even smaller angular scales. And as you can see, the theory matches the predictions all the way out to these incredibly small scales, not only in the variance of the temperature, but also in the polarization of the microwave background. So with these, now we're up to 10,000 measurements, we can see incredible agreement between the measurements and this fiducial model lambda CDM. And as I suggested earlier, we can extract information about the constituents of this universe. For example, one of the constituents is dark matter, and we can pin down the value of the dark matter as a free parameter. When we fit the theory, which has only about 5 or 6 parameters, to the data, we get a value that the dark matter comprises 25% of the total energy in the universe, and the fractional error is about 1.5%. And that means this is a 57 sigma detection of dark matter. That is, it's statistically almost impossible to imagine this happening without dark matter being there. So the second piece of these maps that cements the argument is this evolution when we go from the early universe to the late universe as measured by the dark energy survey. And what I'd like to focus on is the idea that this model, this lambda CDM, once the parameters like the dark matter density are fixed, it makes a 0 parameter prediction for how big the fluctuation should be in the map taken by the, for example, in this case, the dark energy survey. So it's a simple prediction. We can just test it by measuring that prediction. In order to explain what how well the model does with this, I have to introduce kind of a weird parameter. It's called sigma 8. And to understand what it is, imagine placing down in the universe spheres of radius about 30 million light years. In every sphere, you count the fractional overdensity. That is the density in matter minus the mean matter density divided by the mean matter density. So the mean of all those spheres will be 0 by definition. But the variance in that, or the standard deviation of those measurements, is what's called sigma 8. That gives you a sense of how inhomogeneous the universe is. And to repeat, lambda CDM armed with the measurements of the CMB makes a 0 parameter prediction for what we should measure. How can we measure mass when we see only light? We use two techniques. One is we use galaxies as tracers. Galaxies form in overdense regions. And we can also measure the shapes of background galaxies. This is an effect called weak gravitational lensing. That is, as the light from distant galaxies traverses the inhomogeneous universe, it gets distorted so that galaxies near one another are distorted in the same way. And by carefully studying their statistics, we can infer something about the matter along the line of sight. So by using these two techniques, we essentially get two different fields, the galaxy overdensity field and the galaxy shape or ellipticity field. And those two fields, their means are 0, but we can take what are called the 2-point function, or these variances. One is called the angular correlation function, just essentially the statistics of how likely galaxies are to be close to one another. Another 2-point function is what's called galaxy-galaxy lensing. You sit on a galaxy and you see how distorted background galaxies are. And then the shear correlation function, which is the correlation between the shapes of these background galaxies. And that's what I said, what I argued, tells us something about the matter along the line of sight. So I'm going to show you the results of this, and I'm not trying to ask anyone to look at the details of the plot, but I want to make some qualitative results. So these are results from our analyzing half the survey. These came out in 2021. An advertisement is we're finishing the full analysis that should be done in the next couple of months. Please look for that. So the first thing to take away from this qualitatively is that in all these different bins, the theory, which is best fit theory depicted by the solid line, agrees with the data. So that gives us even more confidence that this theory, lambda CDM, works. Second point is there's lots of different data. We're correlating the shapes of galaxies by breaking them up into different redshift bins. The redshift is how far away a galaxy is from us. There's 4 different bins. We can cross-correlate each one with everyone else. So there's lots of different galaxy bins to cross-correlate. There's lots of data. A very important thing that's emerged in cosmology is that we are human beings and we are biased. So traditionally what that means is when we get data, we analyze it. It's very messy. It's all screwed up. And we do all these things to fix it. And if something looks wrong, then we'll fix it until it looks right. And that could end up introducing a bias. Everyone ends up getting the same answer because they're afraid if they publish something that's like way off, people are gonna think they shouldn't get a job or something. So basically, we do these analyses blinded. That is, we don't look at the results or even these types of plots until we do tons and tons of null tests to make sure that the data are not that we have the data at the state we're in. And then we just open the box and see the best fit parameter and publish them. So these blinded analyses are kind of the gold standard for the way to report results now in cosmology. And the final point I want to make is notice the shaded regions on the left. And as following my convention, the left-hand side are small scales and the right side, oh, actually, I changed my convention, sorry. So in this case, the left-hand side are small scales and the right-hand side are large scales. And so the shaded regions are regions we do not use when we make the fits. So we don't consider those regions. Why not? because we cannot make predictions on small scales. The scales that are of order about 5 megaparsecs, which is about 15 million light years. And the reason is we can make good predictions about the theory where things are pretty linear, where dark matter dominates. But as you go to smaller scales, the theory becomes nonlinear. That turns out to be solvable. There's something called an n-body simulation, where you can simulate all the dark matter particles and see how gravity affects them, even as they go nonlinear. However, what the matter, even though there's not in this model lambda CDM, there's a lot more dark matter than there is ordinary matter. We're calling ordinary matter baryonic matter. Nevertheless, this baryonic matter impacts the total distribution of matter on scales as large as a megaparsec or 5 megaparsec or so. That's depicted in this graph here. So what this graph here is the ratio of this variance in the fluctuations, or it's called the power spectrum, as a function of scale. And here I've reverted to large scales on the left, small scales on the right. On large scales, the dark matter simulations, no matter what you throw in when you put in baryons, no matter how you have the baryons behave, they're going to give the same result. But as you go to small scales, it depends, how many supernovae go off, how rapidly they go off, how all these very subtle details of small scale physics are implemented in the code, and different codes and different implementations just give different answers. So we basically don't trust anything on scales smaller than, say, 5 megaparsecs or so. So we're eliminating all that data, and the cosmological results are based on the large-scale data that's not contaminated by baryonic physics. So that's something I think that it will be interesting to hear what Stacy has to say, because I think a lot of the argument against dark matter revolves around physics on the galactic scale. So it'll be interesting to discuss that. Okay, anyway, the result, just to show you that, is that the green curve here is this parameter sigma 8 as measured by the cosmic microwave background. And the gray curve is what we measured in the dark energy survey with our half-year data in 2021. And you see that they agree. That's really an extraordinary agreement. Remember, the microwave background measures the amplitude of the fluctuations when the universe was 400,000 years old. And then the theory, lambda CDM, extrapolates that all the way forward to today, so we can compare apples to apples. And the dark energy survey says we see the exact same, not exact same, it's half a sigma off. It's the same fluctuations in this lensing experiment as we do in the cosmic microwave background. The other thing to notice from this plot is that the x-axis here is the matter density. So the dark energy survey by itself measures that the total matter density is about 30% of the universe. We know the baryons are only about 5% of the universe. So that in itself gives us very strong piece of evidence for dark matter.
You
I'm at the end of my time.
You have about 1 minute.
Well, okay, so I'll just summarize by reiterating these points. So cosmology makes predictions most easily for statistics on large scales. So that means it's easier to write down the theories and to solve the theories on large scales, and we have a lot of measurements, and as a result, we can test theories most easily on those large scales. However, statistics, as you've seen, are technical, they're complicated, and it's hard to convey in an elevator pitch. So it's in a short time. So it's difficult to convey the strength of the evidence. I hope I've tried to do my best. The fiducial model's prediction, lambda CDM's prediction, are an unbelievable agreement with tens of thousands of data points, and dark matter seems essential to that agreement. And the final point is one I've made already. It's very, very hard to make predictions on small scales. So arguments from scales smaller than about 5 megaparsecs have to be treated with caution. Thank you. Stop sharing.
Okay, thank you very much, Scott. And now I will turn it over directly to Stacy.
Okay, now we have the trick of sharing a screen. So let's see if we can manage that. Okay, I hope that looks okay for everyone. Hear no dissent, so I will
Looks good.
say so on. Yeah, the way it's working for me, I don't get to see your faces, sadly. So, all right. Well, thank you for inviting me. It's always a fun thing to talk about, and I thank Scott for giving that great discussion because basically I agree with all that, and I try to go back and forth and put on, you know, a cosmologist's hat and a dynamicist hat, and they're incommensurate. Basically, the evidence that applies is different. And so I've been sort of struggling to figure out, why can we not do that? There we go. How to approach this because I've over a decade ago now, I developed an entire semester course um, on dark matter just to cover the evidence. Because normally when we teach it, we talk about galaxies, and at some point, oh, we need dark matter. Or if we're teaching cosmology, we teach that, and oh, we need to bring in dark matter. So I wanted to go about it the other way around, and there is a section at the very end about modified gravity, and in most semesters I might barely make it that far. So now we're going to skip to the end and try to talk about that. So the need for dark matter, and specifically non-baryonic cold dark matter, some entirely new kind of particle, has been known for a long time. And the big lines of evidence going back before we even had the beautiful acoustic power spectrum that Scott talked about was that we needed to grow the structure in the first place. So you need this growth factor of order 100,000 when it should just be a factor of 1,000 from the redshift which we observe the CMB. And so that right away excludes hot dark matter, candidates like neutrinos if they have mass, which turns out they do, but it's not right. And then also that the mass density that we infer just from how things move out in intergalactic space exceeds the budget for baryons in Big Bang nucleosynthesis. So if we believe those two things, and there's more gravitating mass out there than there can possibly be in ordinary matter, therefore you need some entirely new kind of particle, and you can lop off an entire large branch of baryonic dark matter candidates, which I had scribbled all out there for organizational purposes for my own mind at that point. But even in the 90s or really in the late 80s, people talking about doing microlensing surveys to find brown dwarfs is like, good luck. You know, we know Big Bang nucleosynthesis doesn't allow you to do that. We could have been wrong to assume that, but we weren't. So those chunks of the trees you can cut off. However, it took me a long time to realize this, that we're implicitly assuming that gravity is normal when we make these statements. The linear growth of structure is something that comes naturally out of general relativity. The fact that the mass density looks so big is because we're using gravity as Einstein and Newton taught it to us. And so it's actually a lot harder to exclude the change in the dynamics branch, because then you have to go back and redo all these calculations and see what you would really get. That sounds even crazier than having some new particle. So for a long time, we have assumed that there is some weakly interacting massive particle. That's been the odds-on favorite for years stretching into decades. And the question then that you want to answer experimentally is, do these things actually exist? We absolutely need them in cosmology for the assumptions that we make, which is basically that general relativity is correct, which seems like a really solid assumption. But is that true? And the deeper question that I've struggled with for a long time is, okay, we've inferred that this stuff exists for really good reasons. What if we're wrong? How do we ever, you know, convince ourselves that we went down the wrong branch of the tree here? So is it possible to falsify this notion? And that's very hard. So that's why it's really important to do the experimental tests. This is the summary of WIMP search experiments. So the interaction probability on the left axis and the mass of the hypothesized WIMP dark matter particle on the x-axis. And this whole this whole experimental approach was spawned by the WIMP miracle, which is really convincing, persuasive argument that these things really ought to exist and that it made sense that it gave you the right density. And the original prediction, or really back of the envelope estimate for the interaction cross-section for that, was up around 10 to the minus 39. I've had to extend the axis to include that because that was ruled out a long time ago. I've marked out a revised prediction, sort of loop corrections from around 2008, which has an amusing story, which is why I picked it. But that was sort of what we were expecting for a while, and then the experiments kept getting better and better, and they have succeeded in failing. That they have excluded really all of that sort of expected parameter space. Now, if you're a theorist, it's tempting to keep moving the goalposts to lower and lower cross-section or to much lower mass or higher mass. But if it's something like a normal WIMP, then there ought to be a window to interact through the Higgs. And the statement I hear people make over and over is that the Higgs is too normal. We should see some splitting if they're in this Higgs state, if there's a window into supersymmetry. And so these folks I reference have gone through all the possible combinations of that. And basically, there's just not much room left over for a conventional WIMP. Now, of course, if it's not a WIMP, maybe it's an axion. And if it's not an axion, then it could be something else. So it's really hard to know when to stop. And I just note that we absolutely need it. The cosmology that just works so beautifully, as Scott described, absolutely needs that cold dark matter. It has to be something non-baryonic, something from outside the standard model of particle physics. But it only works if and only if that is a real physical entity and not just something we've invoked to save the phenomena. So can that specific idea be falsified? And so the only thing I'll say about that for now on cosmic scales is that there is this tension. This is the concordance diagram, lots of different cosmological constraints that were important to establishing lambda CDM in the 90s. I won't try to cover them all. But the best fit of the acoustic power spectrum was smack in the middle of this concordance region 20 years ago. So it agreed with every other form of data that we had come up with. And what has changed as the data have improved and we've resolved to finer and finer scales is that it has marched down the trench and chi-squared space to this place where the latest Planck measurement is in tension with these other results, not the age, but certainly with Hubble constant and maybe with some other things. And I'm not going to go through all that. But that's what it would look like if this picture is wrong, is that there's no room left here. And so that's why the Hubble tension is so important, as are the other things. Okay, now all of the evidence that pertains to the specific modified gravity MOND is on smaller scales. And so this is why the data are incommensurate and you have to take a different hat on and off. And first, I wanted to point out that there's already a strong claim made by Ohm and Krupa that the behavior of the orbits of the Magellanic Clouds, these little satellite galaxies of the Milky Way, already falsifies the existence of dark matter halos. And their argument is that basically we measure where they are, we measure how fast they're moving, we know other things about their interaction. There's a Magellanic stream, and the clouds are moving in very fast, but they're plunging through a dark matter halo, which would cause dynamical friction and slow them down. And there's basically no solution that matches all the constraints, which they claim is significant at 6 sigma level. I went through that close enough to say that, yeah, it's an issue doing all that. And like with everything else here, I would question some of the assumptions if I'm going to try to wiggle out of that. But I did want to mention it because Pavel Krupa is very insistent that this is a falsification, and it's not mine. I'm not the one saying that. So what I have to say is about the galaxies. And first, here are some pictures marked out on a graph of the size of galaxies against their stellar mass. So galaxies cover an enormous dynamic range in these parameters, from massive to very low mass, barely more than a giant star cluster, from large to small, from high surface brightness to low surface brightness. So that means high surface brightness means the stars are relatively closely packed, and low surface brightness means they're spread far apart. And that's really an important quantity to this argument. Because where I got concerned about dark matter was in this sort of, I'm going to oversimplify this a bit just for the virtue of time, but if you look at an individual galaxy, it has this famous flat rotation curve. So here's NGC 2403, little picture down there, flat rotation curve. That blue line is what we calculate from what we see for the stars and the gas using Newton's law. And so that is the baryonic mass distribution, the first term there. Really, you have to solve the Poisson equation for a disk geometry, but never mind. The function is like that. It depends on the radial distribution of mass. And you see, that's not enough. We inferred dark matter from this completely different line of evidence because you need something extra to make up that difference, and that's the dark matter distribution. Okay, fine. So there was a well-established paradigm about that before I started studying it. But what I worked on were these low surface brightness galaxies. And by construction, these have a larger radii for the same mass, or basically they're stretched out versions of that. And so if the mass is the same, but the radius is larger, then that baryonic contribution is stretched out, and the amplitude is less, just because R is bigger for the same mass. So what do we expect for this? Well, I had pretty well, at the point I started doing this, developed a theory for how I thought this would work. And so I had made a clear prediction, and I expected the dark matter distribution to be spread out along with the galaxy, and I won't go into the details for that, but that's what I expected. Other people said, no, the baryons are not as masses as you're saying. There's one free parameter here, which is the mass to light ratio of the stars. So you could adopt a lower mass to light ratio, push this whole curve down, and then they don't contribute very much. And you're basically just looking at the rotation curve of the dark matter halo. Now we know from simulations that at a given mass, the dark matter halos look very similar in this respect. And so you basically should just see the same rotation curve for these two different galaxies of the otherwise the same mass. We were wrong. My prediction was wrong. That dark matter only prediction was wrong. And it fails in a really weird way. You end up having the same V flat for the same mass. So it's like you don't care about the radius once you get out far enough. But in close, you do. You do know about the difference between this, and it varies in exactly the way you would have expected. So Newton works here, doesn't work out here, and you can't have both. That's the trick. It gets worse than that, because if you normalize by the size of the disk, so these little dotted lines characterize how big the radii of these are. This is physically a much more spread out galaxy than that one. So if you normalize to that, then those rotation curves are right on top of each other. That's weird. If it were dark matter dominated, I would expect just this. You're just seeing the same halo in kiloparsecs, physical radii. But this is telling us that the dynamics knows about not just the mass of the baryons, but also the radial distribution in a weird way. And so that just struck me as a contradiction, and I could not reconcile it. It's a generic effect. I've showed you that example for two galaxies. But you can look at the residuals from relations like Tully-Fisher, and there are no residuals. Basically, once you get up to V flat, you're a V flat, and that's it for that mass galaxy. And so that would say this term doesn't matter, but we just saw this term had to matter. But if that term matters, then you ought to see residuals along that dotted line. So the only way I could get out of this was fine tuning. And it's a really painful kind of pain tuning. So this struck me as basically a serious problem for dark matter. And I've not heard a good explanation for it since. I've heard lots of explanations, but not a good one. And this behavior is generic. This is an estimate of the shapes of rotation curves. I basically asked, how far up do you have to go before you're at 3/4 of the flat rotation velocity? And so here it overlies about 1. Those are those 2 points right there. But in general, this is true, and fainter galaxies have more slowly rising rotation curves. Models at the time, conventional dark matter models, did something like what these lines do. And so if you've heard of the cusp-core problem, well, that's one way of illustrating it, but it's worse than that. The problem to my mind is not what the structure of the halo is, it's that all you need to know about is the baryons. There's no reference to the dark matter. So here I've color-coded rotation curves by their surface brightness. Red is high surface brightness down to purple being low surface brightness. And you can just see by eye, there's an almost perfect rainbow transition from very slowly rising rotation curves at low surface brightness in to ones that rise very rapidly and flatten out at the high surface brightness in. That is the systematic that needs to be explained, and it's all predictable just from what you see, right? It's just the light that's telling you what goes on there. So it's not just that the rotation curves are flat, but the level at which they flatten out depends on the mass. Big galaxies rotate fast, small ones slowly, and so that's something called the Tully-Fisher relation. On this plot, every point here is one galaxy. The gray points are those with less accurate data. The blue points have more accurate data. The relation gets tighter as the data gets better. And so it's really systematic, and we only knew about needing dark matter for flat rotation curves when we developed the paradigm, but there's more to it than that. And the Tully-Fisher relation just tells you about the total baryonic mass and that outer flat rotation. But you can see there's more information in there, and so the inner rate of rise of the rotation curve correlates with that surface brightness. You can just see that in the raw data. And here's one way of quantifying it that Federico Lelli did. And basically, this is measuring the surface brightness of stars. This is measuring the dynamical surface density, which is basically depends on the rate of rise of the rotation curve. So steep things have high surface densities, shallow rotation curves have low densities. That straight line is 1-to-1. That's what you would get if there was nothing but stars and Newton, no dark matter, no MON, nothing funny business. And that's true at high surface densities, but there's a kink here at a critical surface density, and then you need systematically more dark matter, or more generally, a larger mass discrepancy is observed at lower and lower surface brightness. And that's a critical thing. Anytime we say dark matter, what we really mean is a discrepancy, and it's really hard to distinguish whether that's literal invisible mass or if it's a change in the force law. And there is a great uniformity
You
to
have
these
about 1
data.
minute.
Okay, thanks. That there's this big difference between what is predicted and what is observed in the rotation curve. But if you plot that in terms of the acceleration, what is the centripetal acceleration versus what's predicted, all the galaxies line up on top of each other. And I've been working on this for a long time. This is back before 2000. As we add more data, this relation has gotten tighter to the point where we can't really distinguish things. There are so many points piled on there that we can do the same thing we do with the CMB and bin the data. And there's just one effective force law in galaxies. There's also Renzo's rule, which I won't take the time to explain, but just note that these are systematic relations that other people as well as myself have noticed, and they're consistent with there being a single effective force law in galaxies. Now, it is my great chagrin that Bond actually predicted those things in advance. I would have loved to be able to discover that and say, oh, look what I found. But all these relations had already been predicted before they were observed. That was not predicted by cold dark matter. And there's not a satisfactory explanation for it. If I thought there was one, I would sure as heck say so. So I will stop there. Thanks.
All right, thank you very much. We now move to 10 minutes. Back to you, Scott, and then we'll have 10 final minutes after that for Stacy.
Okay, thanks. So maybe I can start by agreeing with a bunch of things that Stacy said, and then throwing up a couple of points of disagreement, if that makes sense. So first, I agree with what he said about one of the best motivated examples for dark matter are these weakly interactive massive particles, WIMPs, and we've been searching them for 30 years in the laboratory and have not yet detected them. So that has been very discouraging, and I certainly agree about that. I also agree with something I think he said implicitly, but I just want to make sure that we're on the same page, and that is, I said that it's very difficult for lambda CDM to make predictions on small scales, but it does seem to be true, as Stacy mentioned, that when you do these, at least these n-body simulations, almost all the conglomeration of dark matter, let's call them halos, have the same general shape of their density. So as long as you scale the radius appropriately. So this is what this profile typically looks like over many orders of magnitude of radius. It kind of has this one power law going in towards the core, depending on it's a little bit up in the air as to which it is, but both of these fit the simulations well. And then as it falls off, as you go away from it, it has another power. So that's another thing that we agree on, that these dark matter only simulations look like this. I also agree that there's the possibility that we can learn a lot by trying to get to small scales. So let me just reference a couple of an emerging field of near field cosmology. That is, and that's based on the idea that another thing that lambda CDM does, it makes predictions for how many subhalos each massive halo should have. So our galaxy, the Milky Way, is supposedly embedded in a huge halo of dark matter, but embedded in them, the prediction is there should be lots of different subhalos of different masses that have a range of sizes. And as you go to smaller mass subhalos, you see more and more of them. And we're actually beginning to measure those through a variety of kind of complicated techniques. One is looking at satellite galaxies and trying to map their luminosities onto their masses. That's very complicated, but a number of people, including Ethan Nadler, have done this. And then a second thing is to look at stellar streams and to look at perturbations of stellar streams. So I'm really excited about that as a way of probing this theory. So that's where we agree. There's a couple areas where I think we disagree, and that is coming back to this figure. Again, I'm not an expert in this, but just based on the fact that it's so hard for us to predict the matter distribution on scales smaller than 5 megaparsecs, it really makes me nervous when if people are trying to argue that as you go towards the center, the power law should be this or that, because towards the center of the galaxy, there's very, very little mass there. The density is rising, but the total mass is very small. And this will inevitably be, there'll be lots of baryons in the center of the galaxy, and who knows what's going on there. So I'm kind of nervous about any prediction that makes too much of this inner cusp or core. So that's one thing. And then I guess a slightly larger. So I make one more point of agreement, and that is Stacy mentioned something that I didn't, which is if you just have a dark matter only model, then the variance in the matter, the amount by which the fluctuations will have grown since this time of the CMB is much too small, as indicated by these long dashed lines here. And one is nonlinear in these scales. This is, again, large scales, small scales. And you have to get above 1 on small scales in order to produce stars, planets, and galaxies, etc. The standard model does it. It agrees with the data. And there are actually models of MOND, or extensions of MOND, or things in which MOND is a limit of, that enable you to jack up the amplitude and get around this problem that Stacy mentioned. However, those models tend to predict the wrong shape of the power spectrum by just ridiculous amounts. So I'm concerned about any model that reduces to MOND in some small scale limit. I just think it faces a lot of challenges. And then I guess the final, I don't know how much time I have left.
I have about 5 minutes.
Oh, 5 minutes. Okay, so I'll just keep on talking without whatever. Okay. So let me mention also that we do have some information about the mass in galaxies, and that is given by galaxy-galaxy lensing, this probe I mentioned before, that you sit on a foreground galaxy and you measure the shapes of background galaxies behind it. And so I spent a lot of time learning about galaxy lensing. I wrote a book about it about 8 years ago. And so let me just go full screen here. So what the prediction is that if all there was baryons with the normal matter, then as you go far away from the center of the galaxy, the background galaxies, this y-axis here is a measure of the shape and how much the background galaxies are distorted. And that distortion should fall off as 1/r², which is this curve over here. And going back to the Sloan Digital Sky Survey 25 years ago, we actually did not observe that rapid a fall off. Rather, as you went out to a megaparsec or so, we did not see things falling off. So this is consistent with, I think, something that Stacy was assuming from the beginning, that and was trying to disprove, that galaxies live in dark matter halos. So galaxy-galaxy lensing, I think, is very consistent with that idea that the visible matter in galaxies is embedded in these dark matter halos. And so that's very old. And coming fast forward to today, this is one of the 2-point functions I did not show you from the dark energy survey. This is the same thing. This is galaxy-galaxy lensing as a function of angular scale. So we're sitting on foreground galaxies, and we're looking at how distorted the background galaxies are. And now we've become more sophisticated. We've broken them up into 6 different redshift bins for the foreground galaxies and 4 different bins for the background galaxies. And I just can't tell you how much work has gone into these things. It's like the DES itself is 500 collaborators, and we're basing it on dozens of years of work. I mean, I hope someday someone wins the Nobel Prize for weak gravitational lensing, discovered in the year 2000 by a number of different groups, including one of my collaborators, Gary Bernstein. So that's a pitch for him. Anyway, this is a tremendously sophisticated field, really exciting, and it's very rigorous physically. There's no assumptions built in. The assumption is general relativity holds. And so when you do that, you see again that this galaxy-galaxy lensing signal is not falling off as it would be predicted in a normal model. In fact, we've gotten so sophisticated that we're now modeling the galaxy-galaxy lensing signal, again, breaking off small scales because that's hard to model, but we're modeling including not just the single galaxy, but the nearby galaxies that would contribute to the signal. So this has kind of blossomed into a really healthy field trying to understand the relationship between mass and visible galaxies, something that's kind of plagued astronomy for 100 years. And we're now, with the help of galaxy lensing, being able to do that, and that will shed light, I think, even on, maybe someday on low surface brightness galaxies if we can get enough data on that, for example, with LSST. And then my final comment is a philosophical one, I guess. Stacy mentioned correctly that the searches for WIMPs and even the preferred parameter space for the preferred candidate WIMPs is really dwindling. So, you know, and I think you mentioned the word falsifiable. When do we give up on this idea? And I would argue that you know, it's the opposite, really. We've been so blessed with these incredible data streams over the past 30 to 50 years in particle physics and astronomy, and we've learned so much. We can, if you think about where we were, you know, 100 years ago, you know, Einstein didn't have the courage to predict the expansion of the universe. Even he didn't have that audacity, and now we're at the stage where we have this incredible model that fits all this data. So I think we have to have patience, and in some sense, I think that's true for not just our field, but fields like particle physics that have, you know, taken a century to develop this diagram on the left. Search for you know, extraterrestrial intelligence. I don't think anyone's suggesting we should give up now because we haven't seen anything yet. And you know, other deep questions like consciousness, AGI, etc. I mean, these are very, very hard questions. Cosmology is a millennial old science, and the fact that we haven't discovered anything in a couple of decades is not. I mean, it's certainly discouraging to people like Orin who are betting their careers on it. But to us as a civilization, I don't think we should be that shocked that we haven't found it yet. So that's my pitch. Yeah.
Thank you, and back over to you, Stacy.
Okay. So there's so much to say, and I would like to start by agreeing with the philosophical point that we can't expect these things to happen like that. But that's also true for the development of theory. If you want to build a theory that encompasses both general relativity and all its well-known successes, as well as a strange theory like MOND, that's not something you can do on the back of an envelope. It'd be nice if you could, but you can't expect it to happen overnight. It takes a long time, right? The Poisson equation is something that I use a lot in my work, and that's not the Newton equation, right? It takes a lot of intellectual development to get from one to the other. So one problem that modified theories had was light bending, so gravitational lensing. And the first theory to properly do that was Tevis by Bekenstein, which didn't work. Scott showed that for reasons he alluded to with the acoustic oscillations. It also did not give you the right microwave background spectrum. So I think an important advance to point out is that there is now an Ether-Einstein, Ether-scalar tensor theory by Skordas and Volosnik, which basically reproduces the lambda CDM fit. So that's what you're looking at now. Whether that theory is right or not, I don't know. I have some reservations about it, but it's a really important demonstration that it is possible to get a fit this way. It doesn't have to be literal cold dark matter. It could be some other kind of degree of freedom in one of these kinds of theories. So we agree about that. It's just, you know, coming at it from different directions. And so I think the thing that I want to emphasize that keeps me thinking about MOND is why it gets any predictions right at all. If we live in a world dominated by cold dark matter, that really shouldn't be the case. And so I told you about some predictions, and a lot of those were all priori predictions, truly gold standard stuff. And I want to mention, just so you're aware, some of these other things, because I keep trying to test it. One of which is the stability properties of disks. A spiral galaxy by itself is not stable. And in order to stabilize it, you have to put it in some kind of deeper potential well, and i.e. a dark matter halo. Peebles and Ostreicher showed that 50 years ago. And that was really important to the development of the field. And so, that's something we have to reproduce. So if you look at these low surface brightness galaxies I work on, they're these sad little things, but they do sometimes have spiral structure, quite often actually. And you can do the calculation and see how much mass you need to make that go, because it's a competition between the instability of a thin disk and stabilizing influence of a spherical halo. And you have to get that balance right. And you can do that in high surface brightness galaxies, but then it doesn't work for low surface brightness galaxies. Oh, except in MOND. That predicted that. The thing I like about MOND as somebody who works on individual galaxies is that you can look at an individual galaxy, something we can't expect to do with large-scale simulations, right? All you can do there is say, okay, I've simulated these objects and they will have these properties, and then you can make statistical comparisons to observe galaxies. But just as in the solar system, where you can say, okay, there's that moon around that planet. I can calculate how fast it's going to go, knowing how fast, how massive the planet is. You can do the same thing for individual galaxies. I can look at one galaxy and tell you how fast the stars are going to be moving. And this is all the satellites of Andromeda. I realized a decade ago, as the Panda survey was being done, that there was the opportunity to make that true a priori prediction, that is, predict what the speeds of the stars would be before they were measured. And people were doing the follow-up work so fast that actually some of these were really gold stars because they published it faster than I could publish it, even though I'd already done the calculation. But the point is, you can look at a galaxy and say how it's going to move, just like you can apply Newton in the solar system. And that works. Okay, Andromeda 5 didn't work, but that works over and over and over again. And I have tried to do this in Lambda CDM, and I just can't. And it's for the reason Scott said, you just can't really make a clear prediction that small. Okay, but why did that work? This is the last thing you'd expect. It's like, if somebody told you the solar system worked on an inverse cubed law, it just looks like an inverse square law because the dark matter is distributed just so. It's just the worst possible fine-tuning problem. There's another example. Clusters, I want to point out, clusters are a real problem for MOND. They are offset from this Tolley-Fisher relation. So this is what this shows. Now you have to zoom in to tell that they're offset from the line, but that offset is real and statistically meaningful, and it's been persistent for a long time. And that's why you have things like the bullet cluster. That's just a special case of this more general problem. In the residuals, you can see there's an offset, right? So, okay, that's a problem for MOND. Doesn't get the mass budget right. The mass budget actually works out in Lambda CDM, at least for the most massive clusters. However, the slope of this relation, you notice the slope is parallel. That is not what it should do in Lambda CDM. It should have a different slope. And that's why that dashed line representing Lambda CDM does something different. And you notice it deviates even for low mass clusters. It's already off. Another thing that MOND does well is make things move fast. And so the collision speeds of clusters, like the bullet cluster, can be faster than is technically possible in straight Newtonian gravity. So it actually does that part better. So, if I want to put on a dark matter hat, I say, aha, this falsifies MOND, and maybe it does. But if I want to put on a MOND hat, I'd say, aha, this is naturally explained by MOND. It really doesn't make sense in dark matter. So I'm just confused by clusters. There is also the missing baryon issue. The baryon budget, i.e. the cosmic fraction of baryons, is that represented in each individual dark matter halo. That works out okay for clusters, and we can play with this normalization. I'm not concerned by that. But for smaller things, we're nowhere close. For even Milky Way mass things, let alone dwarf galaxies, there should be a lot more baryons associated with the dark matter halo than what we actually see. Okay, they don't have to be all lit up, but this is a very tight relation. And what's weird, again, is there's a fine tuning. You always have to put things exactly on this line. In Bond, it's the other way around. What you see is what you get until you get up to the clusters, and then that offset that I showed you causes what might be a missing baryon problem in Mond. That's one way you could address that problem. I'm not very convinced by that. It's just confusing. But still, while you're getting the total dynamical mass wrong, you're getting the collision velocities right in a way that's really hard to explain in dark matter. And these are not particularly small scales. People have tried to build models that explain these data. I find them pretty underwhelming. I've tried it too. So that green line, Pingfei Li was a student of mine. So we got something very similar to what Oman et al. Did there. And you basically end up, once you get out far enough, paralleling that. Newtonian prediction is just Newton plus dark matter. Brouwer pointed out that that's not really what it looks like for the lensing data. And she was specifically looking at isolated galaxies with lensing. And I thought we could do better. So to be as
You have about 1 minute.
Basically redid that analysis, did a number of improvements, and then you see basically one continuous effective force law. And so this may be a point of disagreement with Scott, is that the lensing signal that we find is pretty Mond-like. And if that is correct, it extends the flatness of rotation curves to ridiculously large scales, nearly a megaparsec, and importantly, beyond where you really ought to see the rotation curve declining for dark matter halos. So the question to me, another thing we predicted, all the JWST observations, those galaxies at high redshift are too massive. That was predicted in the last century by Bob Sanders. The JWST data, the high redshift data, look exactly like he predicted. And this is a critical test because lambda CDM, right? You start out with all these tiny things. This is fundamental to the paradigm that you're building up structure hierarchically, and that takes a long time. And that is not what we're seeing. So what we're seeing from JWST is consistent with a nonlinear growth rate at those early times, which is what you get from Mond. So I will leave you just with that philosophical query. Why does Mond get any prediction right? I would be very happy if we detected dark matter tomorrow, and then we would know. And it's certainly true that we shouldn't expect to do that right away. But that's not what bugs me. What bugs me is that this stupid theory keeps getting these really different predictions correct, and they're really hard to do within the context of dark matter. I've tried. And so I will leave it there. Thank you.
Thank you very much, both of you. This is one thing I really liked is that both of you kind of focused on different scales, which kind of naturally leads me to one question while we wait for anyone else that wants to ask questions in using the Q&A feature. So I guess one question I have for both of you, I'm a little biased. I work in the field of dark matter, but my own bias is that kind of independent of astronomical data, independent of theory motivations like supersymmetry or the strong CP problem, that it's plausible that some weakly interacting particle has gone undetected, right? But conversely, like even if dark matter were detected today, I still think one should be open-minded to the evidence for Mond that Stacy has described. So I guess my question for both of you is like, to what extent do you think that these research programs can coexist? Like it's something I don't ever hear about. Like, have people tried dark matter plus Mond models to see if there's better agreement, with the, can you solve both of the problems you've mentioned simultaneously with both?
Do you want to do that, Scott, or shall
We can take turns. I'll go first. Or you can go first. I don't care.
Well, I don't care, but the answer to my knowledge is yes, people have tried this. Perhaps the leading example is the neutrino, sort of dark matter Mond hybrid. I am not a fan of that because it's just invoking sterile neutrinos to play the role of cold dark matter, and they're just not cold enough to stick to galaxies. And that's critical because if you have a reasonably massive, weakly interacting massive particle and a Mond-like force law, then they're going to stick to galaxies like crazy, and then you'll have way too much mass, and then Mond won't work. Basically you destroy the virtues of what it does. So I don't. There are also hybrid models like Curie's superfluid dark matter or Blanchet's dipolar dark matter that endow the dark matter particle with properties that naturally give you Mond-like phenomena. That I think is worth considering, but there are very few of those.
Yeah, I guess my take is I think 99% of the simulations run have dark matter in them, and that's because the community basically can't see a way to get or isn't really convinced of any of the arguments from very small scales, or doesn't see a way to get anything close to reasonable if you don't have dark matter in the simulations. So I think people vote with their feet, and they're voting that, at least now, that it, lambda CDM's right, and Mond, either the successes. I actually don't understand the successes that well, but they don't. I spent some time studying them, and they were not that compelling to me. And my guess is that's what other people feel as well. It doesn't mean we couldn't be wrong, but I think that's what people are voting now.
Well, I think we're talking like that, right? We've come at it from different scales and different things. And so,
But I guess where we're really disagreeing is you seem to be saying that lambda CDM fails on small scales, and I'm saying it doesn't fail because it doesn't make predictions.
well,
And it can't make predictions on small scales.
so
So that's where I think we're disagreeing.
I would say the same thing about Mond for cosmology. One of the annoying things for Mond is you don't even know what the background cosmology is. So you can't do that kind of simulation unless you just assume it, put it in by hand, which people have done. And, you end up getting large scale structure that looks more or less like, it's just a magnification of Newton. So it does many of the same things. The timing is different. So you get big galaxies early. But the issue to me for how to test dark matter on small scales is it's not quite as bad as you say. I mean, people have worked pretty hard to make galaxy simulations. I agree that there is no clear testable prediction. That's a great frustration to me. But we know that the dark matter halos have to be cuspy, and we know that's wrong. So the game that the simulators play is how do I fix it, not how do I make a testable prediction. And I find that frustrating for the reason I tried to express, which is that I can predict something for a real universe object, and I get the right answer without knowing in advance. And just like I can do that for binary stars or any Newtonian system, and I can't do that with dark matter. And so why, if it's dark matter that's doing it, why does it always look like this stupid force law? And it is stupid, right? It's just a crazy idea. And that makes no sense. That's the only thing I can say about it. If you say, oh, well, I don't make the prediction, that's true, but that's the same thing for Mond. And then we're just talking about completely different things. But to go back to Orin's question, I don't think you can really make a hybrid. I just don't see how you do that. I hope I'm wrong, but I don't see how.
One user asks about a couple. One named Tyler asks about an individual galaxy. Yes, when we are checking the paths of objects in rotation, do we use vacuum solutions, i.e. the Kerr metric? And if not, what is the standard way of deciding if there's a discrepancy between theory and observation? And I would myself piggyback onto that to ask about individual galaxies, because one might think that for an individual galaxy, if you found one without, say, dark matter discrepancy, then that would be a falsification of MOND. And I hear in the news, someone found a galaxy without dark matter. Maybe that would also just be a way for you to describe the difficulty of measuring these things about galaxies with confidence. That might be interesting.
It would be interesting, but you don't want to sit here that long. So the quality of galaxy data varies substantially. And so for the most part, the claims that I've seen of deviations from MOND are low quality data. And as the data improve, those claims diminish. And I don't say that lightly. I've been following this for 30 years, and I have investigated literally hundreds of individual cases where that has been the case. Now, there are always some that are genuinely concerning. I made that point about clusters. There are a few individual galaxies that concern me. NGC 1052 DF2 is one of the famous ultra diffuse galaxies in that respect. And I would say that if they had shared the photometric data with me ahead of time, I could have gotten the answer right in that case. But there are still, I mean, I actually had a program where I went out looking for things that should be sheared of dark matter in tidal encounters. That can sometimes happen. Because having a dark matter free galaxy makes no sense in terms of dark matter any more than it does in MOND. But in a tidal interaction, you at least have a mechanism where you can have that happen. And we found some examples. And so we were all set to say, okay, this falsifies MOND, because that was what we set out to do. And then Federico Lelli, my postdoc, was like, let's check the timescales. And basically, the signature was that the rotation was too slow. There was no extra mass needed from what we saw. But there had only basically been time for 1/2 of one orbit in the best case galaxy since the tidal interaction that we thought made it had happened. That is to say, it hadn't had a chance to settle into dynamical equilibrium. So that speed was not measuring necessarily what we had hoped it was measuring. So we were just like, ugh. Well, we still reported that, it's in the literature, but that's one of the things you got to watch out for is, we are assuming that the dynamics are in dynamical equilibrium when we do these kind of calculations, and that's not going to be true for every single galaxy. So there's lots of things you have to worry about like that.
So if I could just add on to that or respond to what Tyler asked, I'm pretty sure the answer is we just use Newtonian or Mondian gravity. There's no GR or any fancy metric here when analyzing galaxy.
Yeah, you don't need that.
All right.
I mean, and you'd love to have the combined theory, of course, but it's not how it's done.
Yeah, I mean, I recall just being interested in that question myself. Like, does even just special relativity play a role in, time dilation or something? And yeah, back of the envelope calculation, I think, shows that it's not a very important factor. Let's see. All right. Anastasia asks, this is for Scott. Would you agree that originally the main evidence for dark matter came from galaxies, but not anymore? And this seems to be leading to the second part of this question about a lot of people maybe aren't as familiar with the cosmic microwave background evidence. They ask, I am not sure what you mean by the prediction of the CMB power spectrum. The second peak was predicted incorrectly and then accommodated by changing the baryon density and thus leading to the lithium problem. So how can it count as a great success for lambda CDM?
Yeah, I agree with the first point that she says, or they say that the original motivation, Vera Rubin's measurements led people to introduce it. The second thing, I guess I'm a little skeptical of that. I take your point that after the second measurement of the second peak, the baryon density was higher than people thought from Big Bang nucleosynthesis a little bit, but now they agree extraordinarily well. I mean, it's unbelievable how well the measurements of the baryon density from nucleosynthesis and the CMB measure. And again, I'm not sure about the BBN people, I'm guessing they do this also, but we're doing everything blinded. So I'm not sure, and I don't really understand. I take Stacy's point that it must be intensely satisfying to be able to look at an object and model it and get your hands on it and really understand what's going on in that object. I'm just not convinced that where we're going to get the most science out. And I'm also not sure if people are doing things in a blinded way. In the CMB they are, and that gives me a lot of confidence that they're not just tweaking things to get the post-diction instead of a prediction.
Let me share something quick. This was in a bonus slide deck. This is what Anastasia was alluding to. So currently, deuterium is in good agreement with the best fit baryon density from the CMB. And that then tells you what the lithium abundance ought to be, and it's that red band. That's just not what we see in stars, and for a long time we've assumed that that's just something weird about stars. Very recently, see the same thing in the interstellar medium in the Small Magellanic Cloud. And so that is a real tension in BBN. I don't think BBN is wrong, but I do think there is some systematic error, and it's not obvious to me that it has to be in lithium and not in deuterium. And so the other part of that, that she was alluding to is that way back before we had good acoustic power spectrum, I did try to use this as a distinguishing technique and predicted what the ratio of the first to second peak would be. And for BBN, as we knew it at the time, including deuterium at the time, basically what we observed was bang on what I predicted for no CDM. And it was outside the range of what was expected for lambda CDM. And that includes deuterium beforehand. And you're concerned about blinded things. If you look at just and I've made this plot, I've published this plot. If you just look at the baryon density by each element, basically deuterium does a big step right when the CMB data became available. So I hope that's not confirmation bias, but that's sure what it would look like if that's what we're going on. Because the deuterium abundance fell immediately into line with CMB best fit, which had to go outside of what we had established as the bounds for BBN. Not by a huge amount, so I don't know how important that is. But it's striking to me that the first to second peak ratio is bang on what I predicted for the case of no CDM. That said, the third peak is much too big. And that, to my mind, is the biggest reason why you need cold dark matter or something extra, right? It could be a scalar field in one of these modified theories or something like that. So I just don't know what to make of that anymore. But I do know from doing a lot of spectroscopic work that it would be really easy to have a large systematic error in the deuterium abundance. I don't know if that's what's going on. People have done a lot of really tremendous work, and it is very precise. But I'm not sure how accurate it can be, because you have to know the continuum extraordinarily well, because you're comparing this completely saturated primary hydrogen line to this little bitty weak deuterium line. If you get the continuum level just a tiny bit wrong, that changes that ratio enormously. And we know there were systematic errors in the 90s because Craig Hogan's group got a completely different answer than Tytler's group, and neither of them got the same answer that people get now. I hope they have it right now, and I don't actually have a strong opinion or care too much one way or the other. I just worry that we've forgotten about lithium as a thing that needs to be agreed on. So when we say everything works great, we're forgetting the things that don't work great, because there are some.
We have a number of questions about the recent JWST data. I know you already mentioned this, Stacy, about the early galaxies, more massive than we'd expect. I don't know if, Scott, you have any opinions on that?
No, I don't know.
So,
Go ahead.
yeah, so again, I mean, whenever I do this, I go through all the conventional dark matter-based explanations. And this is another case where you can explain the JWST observations, but you have to do untoward things. So basically, what's well predicted by lambda CDM is the hierarchical assembly of mass. That doesn't do it. If that's all it is, then it's wrong. But what we observe is not the mass, it's the light. And so we have to have some kind of modeling process that involves lots of complicated astrophysics that assigns light to the amount of mass we believe to be assembled. And so there are lots of knobs there that you can turn to try to match the data. That said, none of them make much sense. I've done this exercise, and yes, you can do it, but you end up with very silly models. So how silly do you want to be? If you're not concerned about your astrophysics being silly, sure, no problem. But if you are concerned about a priori predictions, well, then it flunks. We knew what the assembly should be. We know what we thought the astrophysics would be, and that's not what we see. Whereas in MOND, we had a prediction. We have the same astrophysics, and it gets the prediction right. And it's just my experience that this has happened over and over again. So again, to me, it's not that dark matter fails to make the same predictions, because that's certainly true. It's just that why does MOND work at all? That's weird. Shouldn't.
Do either of you have any upcoming data or analyses or experiments that you're excited about that would help inform this debate, and or any pre-registered guesses of the outcome, or whether they would steer you in one direction or another on this question?
You want to go first? Or if nothing, I'm happy to go either way.
Go ahead, Scott.
Okay. Yeah, I mean, I actually don't think it's an open debate. I guess I said, I think the evidence is pretty compelling right now for lambda CDM. However, what's exciting to me is the possibility that it's wrong. Not that MOND is right, but that it will have to be completely replaced. I don't see a way to do that now. I don't think anyone does. But if, for example, the tensions that we're beginning, Stacy alluded to one, this Hubble tension. So if that persists, that could mean we're wrong. And I really am against the notion of adding epicycles. We've already added dark matter, dark energy, inflation. So we added just to the standard model of particle physics 3 new things in order to fit the data. And that, it fits extraordinarily well. And so we've given ourselves a pass. But doing more than that, I think is going to stress me quite a bit. So if it's really true that the Hubble tension persists, or a few weeks ago, or actually last year, DES supernova came out and they were in tension with DA supernova and BAO came out and they were a little in tension with lambda CDM. So we're desperately searching for tensions that can break lambda CDM. So I don't want anyone to get the impression that, oh, I'm satisfied with lambda CDM, I'm thrilled every time it gets confirmed. It's just the opposite. Most of us who are working in this field because we believe the data lead us here are desperately looking for tensions that could break it. And then once it breaks, then things will open up and hopefully will be led to alternatives that will replace it. But we need really challenging new ideas. My opinion is MOND is not one of them. I've looked at it I spent 5 years of my life looking at it, and certainly not as much as Stacy, but I found it very uncompelling. And so what we're looking for, though, is something that can replace what seems to be pieced together. And if there's any tensions that persist, I mean, anytime there's going to be a few tensions, so we have to be willing to live with that. However, so right now the lithium tension or the H0 tension, I think that's inevitable for a theory that that those could go away in the next 10, 20 years. But if those persist or get stronger, or get more compelling, that will be really exciting, because that will mean we don't know what we're talking about, and that will mean that we have to look for something completely new, and that will really open up the field for new ideas. So that's what I'm most excited about, that possibility.
So I agree with most of that. I guess I would add that we all have to make our own standard for what would falsify the standard picture, what would be compelling enough to make us abandon that. And for me, it wasn't that I found MOND compelling. It was that I had run into these fine-tuning problems that I described. And you mentioned epicycles. I worked incredibly hard to try to explain these things. And I couldn't do it without fine-tuning. And every time I thought I had done it, I realized I had made a tautological module. I had assumed the answer I wanted somehow, somewhere in the model. And I spent what seemed like an eternity running in that loop. And so you mentioned epicycles. That's what it felt like I was doing, was adding epicycles to my dark matter models to make these things work out. That's how I remember thinking about it. So that is a unique position I was in, that I was already struggling with that when I became aware of MOND. I didn't know about it before that. And it was just a chance encounter in Middle Earth, basically, literally in Cambridge, that Milgram came through and gave a talk. And I remember seeing the poster and it's like, oh, modified gravity, who wants to hear about that nonsense? And I almost didn't go, but then he basically, in a few lines, derived all the things that I was finding epicyclic in my own modeling. So the compelling part to me was its ability to explain things that I could not explain conventionally. And I will add to that you can, a lot of what I see going on in the galaxy scale dark matter discussion is sort of divide and conquer. Oh, we can explain Tully Fisher, or oh, we can explain the diversity of rotation curves. But you can't actually do that simultaneously. And, you know, if you've only done one, you're like, good enough. And so we basically have a consistently low bar for lambda CDM because we're already convinced it's right. We have a justifiably high bar for MOND, but it's basically passed all those tests except for clusters. But the real question for it is making it an acceptable theory, right? That would actually let you answer these questions in cosmology. And my hope is that if there is such a theory, that then these other things, like you said, we've already added dark matter, we've added dark energy. Hopefully all that just falls out of the right theory. But we're not going to discover that unless we put a lot more effort into building those kinds of theories. Right now, people are strongly discouraged from thinking that way. So I'm worried that we're in a rut and we're going to stay in that rut, because how do we get out of the rut is the question. I don't think either of us actually responded to the prompt, which was what new data are you looking forward to. My group is building a much larger version of the Spark database that was limited by 21 centimeter observations to 150 or so galaxies. We expect to get well over 1,000 now. And so, you know, I expect to see more of the same. But if you explore a lot more galaxies, maybe you'll find something different and things that deviate from the relations that we've seen.
Well, thank you. I should try to start bringing this event to a close, but if either of you have any last things you'd like to, that you're eager to say, give you the opportunity now.
Nope, I'm good. Thanks very much for giving us the opportunity. This was fun.
Yeah, I think I'm eager not to say anymore, but I appreciate all the issues, and it's just frustrating to me. There's a tendency for famous scientists to appear to figure, oh, I've reached the end of my career, there's nothing new to discover. There's clearly a lot to be left to be discovered. And so my fear is that I won't live long enough to see whatever the solution to these problems might be.
Great. All right, well, I do have a note to say that a video recording of this event will be posted on the NEIU Library's YouTube channel within the next few days. And everyone, please give me or join me in giving a virtual round of applause. I know that you don't have mics, but thank you both of our speakers. I really enjoyed this discussion.
Thank you, Orin.
Thanks, Orin. Thanks, Stacy. Bye-bye.
Bye.
Ciao.